You may not realize it, but we're surrounded by arguably the greatest, most revolutionary invention of the last 50 years. It's in TVs, stereos, watches, cars, phones, traffic lights, and pretty well every appliance in your kitchen. In fact, these days, if a device uses electricity, it probably uses one. The tiny gizmo in question is, of course, the silicon chip. Making these extraordinary miniature electronic brains is one of the most complex manufacturing tasks ever attempted. So how do they do it? Texas, USA. Home to big stuff. Big cows, big boots, big hats, big moustaches. But Texas is also the birthplace of a miniaturized miracle, the silicon chip. And here in Sherman, 30 kilometers north of Dallas, is the MEMC fabrication facility. Here in this strange, futuristic-looking plant, they produce silicon wafers, which are the basis for all modern microchips. Silicon has special properties because it's what's called a semiconductor. That means, depending on how it's treated, silicon can either conduct or block the flow of electricity. It's this property that makes it perfect for supporting the millions of tiny transistors necessary for a modern computer chip. The trouble is, because these transistors are so incredibly small, the silicon base on which they rest needs to be absolutely perfect. It took decades to discover a way to produce silicon with a perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heat it to 1420 degrees Celsius inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is then spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, is lowered into it while spinning in the opposite direction. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at around 1.5 millimeters a minute. The result is a single silicon crystal weighing around 200 kilos and with a diameter of around 200 millimeters. The crystal is so strong, its entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. So, after testing with chemicals and X-rays to check its purity and molecular orientation, it's fed to a silicon salami slicer. This 10-ton wire saw uses a fast-moving web of ultra-thin wire to produce wafers of silicon that are just 2/3 of a millimeter thick and 99.99999999% pure. But once cut, there are microscopic marks left on the wafer's surface. So it's time for a buff-up using a process called lapping. But even after a twirl in this high-powered polisher, they're still not smooth enough. So they're then given yet another buff using a chemical process. The result is wafers of silicon with a surface roughness of less than 0.1 billion billionths of a meter. Buffed to a sheen, they're now ready for etching with the circuit design. Packing millions of transistors onto these tiny wafers is the job of chip manufacturers like Texas Instruments. Back in 1958, the inventor of the integrated circuit, Jack Kilby, managed to squeeze a single transistor onto his design. These days, the latest generation use almost 1 billion, and according to Moore's law, that number doubles every 2 years. But of course, the more they try and pack into the design, the smaller each transistor needs to get.
There are over 250 million transistors in this design, someone has to shrink them down to this.
Working at this microscopic scale exposes the chip makers to a major problem. When a transistor is only 1/10,000th of a millimeter across, the smallest particle of dust is enough to cause an electronic train wreck. So, before staff like Dane Bailey set to work in the fab, it's on with the bunny suit.
Wafer fab stands for wafer fabrication. We build the chips here. We start with the bare silicon wafer. We run through a multitude of different processing steps. For our general product that we make here, a DSP, typically takes on the order of about 1,500 individual processing steps from start to finish.
With an area of just under 18,000 square meters, the fab is a Class 1 clean room. Thanks to 12,000 tons of air conditioning equipment, the air is 1,000 times cleaner than a hospital operating theatre.
There's actually less than 100 particles per cubic foot of air. As few as one particle landing on a critical area can kill a chip.
To give you an idea how clean this room is, walking alone produces 5 million particles every minute. So, to avoid contamination from the inadvertently dusty staff, front-opening unified pods, or FOUPs, ferry packets of wafers through the intricate process of component construction. The key problem is miniaturizing the complex designs and imprinting them on the wafers. It's done through a process known as photolithography. First, the wafer is coated with photosensitive chemicals, which harden when exposed to UV light. In sealed darkrooms, light is shone through an image of the design, then through a miniaturizing lens and onto the coated wafer. When the chemical is washed off, the design remains, just like a developed photographic image. But in order to pack all the components onto the wafer, they're built up layer by layer, like floors in a miniature skyscraper. So, to complete the job, the FOUPs cycle the wafers up to 40 times, repeating the photo-etching process for each new layer. Some layers are cooked, some blasted with ionized plasma, some bathed in metals. Each different type of treatment changes the properties for that layer and slowly forms part of the jigsaw making up the chip's design. The finished sheets of silicon wafer carry up to 1,000 individual microchips and over 4,000 billion circuit elements. All that remains is to slice and dice, and the journey from sand to circuit board is complete. What was once a worthless pile of sand can now change hands for more than $17,000 a gram and calculate pi to 1,000 decimal places in the blink of an eye. Metaphysical poet William Blake reckoned he could see a world in a grain of sand. But if he were to look again now, he would surely be even more amazed to discover 1 billion tiny transistors.